A geologic formation near Aix-en-Provence, France, is famed as one of the world's chief treasure troves of fossil species from the Cenozoic era. Since the late 1700s, scientists there have been unearthing amazingly well-preserved fossilized plants and animals. Because arthropods, animals with exoskeletons like spiders, are rarely fossilized, their abundance at Aix-en-Provence is remarkable. A new study in the journal Communications Earth Environment from researchers at the University of Kansas is the first to ask, what are the unique chemical and geological processes at Aix-en-Provence that preserve spiders from the Oligocene period so exquisitely? It's hard to become a fossil. You have to die under very specific circumstances, and one of the easiest ways to become a fossil is to have hard parts like bones, horns and teeth. So, our record of soft body life and terrestrial life, like spiders, is spotty. But we have these periods of exceptional preservation when all circumstances were harmonious for preservation to happen. Alcott and her co-authors Matthew Downen, then a doctoral candidate in the Department of Geo. Matt was working on describing these fossils, and we decided, more or less on a whim, to stick them under the fluorescent microscope to see what happened, Alcott said. To our surprise they glowed, and so we got very interested in what the chemistry of these fossils was that made them glow. If you just look at the fossil on the rock, they're almost indistinguishable from the rock itself, but they glowed a different color under the fluorescent scope. So, we started exploring the chemistry and discovered the fossils themselves contain a black polymer made of carbon and sulfur that, under the microscope, looks like the tar you see on the road. We also noticed there were just thousands and thousands and thousands of microalgae all around the fossils and coating the fossils themselves. Alcott and her colleagues hypothesized that the extracellular substance these microalgae, called diatoms, are known to produce would have protected the SPID. Vulcanization is a naturally occurring process. We do it ourselves to cure rubber in a well-known process, Alcott said. What I think happened here chemically is the spider exoskeleton is chitin, which is composed of long polymers with carbon units near each other, and it's a perfect environment to have the sulfur bridges come in and really stabilize things. Alcott said the presence of diatomic mats may potentially. So, we're wondering if this explains most of these fossil sites that we have in this time, basically from soon after the dinosaurs went extinct until now. This mechanism could be responsible for giving us information to explore the evolution of insects and other terrestrial life post-dinosaurs and to understand climate change, because there's a period of rapid climate change and these terrestrial organisms help us understand what happened to life last. I honestly think this study is partially a result of pandemic science, she said. The first batch of these images showed up in May 2020. My lab was still closed. I was 2 months into my leg of 18 months at home with kids all the time, and so I had to change how I was doing science. I spent a lot of time with these images and these chemical maps and really sort of explored them in a way that they probably wouldn't have happened if all the labs were open and we could have gone in and done more conventional work. Alison N. Alcott, Matthew R. Downen, James D. Schiffbauer, Paul A. University of Kansas. 2022, April 21. Glowing spider fossils prompt breakthrough study of how they were preserved at Aix-en-Provence. Science Daily. Retrieved April 21, 2022 from ift.tt/4csas3m University of Kansas. Thanks for watching. Please subscribe my channel for more videos.